All right. So we finished by talking about this kind of complicated, seem to be complicated method, but it's not really, which what we are going to solve the project with, and it's called the effectiveness method. I would like to solve a problem on this method, but let's just review it very quickly. So this method basically comes down to this, that epsilon is called effectiveness, and it's a measure of, epsilon is a measure of Q actual over Q max. So when epsilon is 1, you made your dream. You managed to do what? You managed to take the hot fluid down all the way to the cold fluid, or you managed to take the cold fluid all the way up to the hot inlet temperature. Whoever is minimum, whoever have m dot Cp minimum, he will be able to do this, and that would be Q max. Right? So Q max is C minimum THN minus T cold N. Right? And from that ratio, you can get your Q. You can get basically what this heat exchanger is capable of transferring. So this method is really perfect when you don't know the Q. You just have the hot fluid coming, you have the cold fluid coming, and you are just wondering how hot will it get. The previous method, the logarithmic mean temperature difference method, was perfect if you know the 4 temperature. And you're just trying to size the heat exchanger, just trying to find out what is the area of that heat exchanger that I need to buy. But if you don't know the output and you actually have the U and E, and by the way, the U and E is here. So we said, we finished last time, we gave a free quiz, free homework last time for saying that the area is actually here inside this epsilon. So the C over C, C minimum over C max, and the number of transfer unit, which is basically AU over C minimum. Those two guys, through the equations or through the chart, will give you this epsilon. All right? And from that, you can tell how much is the Q. All right? And then you'll be able to tell how much we will actually be able to do for you. And so there are all those equations for epsilon or charts for epsilon. All right? So either the equation or the chart, you would use them to come up with this epsilon. All right? And notice that every one of them have C minimum over C max. So you have to decide before you use this chart who is minimum and who's max. So the method become not really that nice, not that friendly when you don't know the m dot or the CB of one of them, like our project. So what makes our project annoying is that we are asking for the m dot, and still we have to use this method. Well, you will have to assume that one of them is minimum. Right? And assign this number before you are actually able to use the chart. All right? But because you are using Excel, that assumption gets verified very quickly. And when you look at that video, you will see that basically in 4 lines, maximum 4 lines, Excel is doing them. Your assumption get reused and reused and reused until the number that you assume is exactly the number you calculate. And then the problem is over. Okay? So the turn error is really that easy. And once you learn how to do this, then you can solve any nonlinear set of equations that way. You just start with assuming one of them, and you calculate the same variable at the end. And you check, does it match? No? Let me go again with a new value. All right? So the extra part that's annoying, so see, if every one of them, you have to decide who's minimum and who's max. But in the cross flow with one of the fluid mixed and one of the fluid is unmixed, you will actually see 2 sets of equations or 2 sets of graphs. Of course, if you use the equation, just use the right equation. But those graphs stand for one of them. So you see the black one is 0.025, 0.5, and 0.75 and 1. While the dotted one is 1.3, 2, and 4. And it has to do with the 0 and the infinity. All right? So who's the mixed and who's the unmixed? The minimum and the max. We'll talk about this later. But let's solve an easy example first. And go back to this. It's not a quiz. We'll actually have a quiz after we finish this example. Right. So, because I still know this method is confusing, it was confusing for me when I was a student. Let me just do what we just said in a graph, because that helped. So that epsilon, and here is the UA over M dot C minimum. This, the whole thing is called number of transfer unit. And that's the x-axis. All right? And those graphs are for different C minimum over C max. Okay? And this epsilon again is Q dot over Q dot max. And this, of course, this Q dot could just be M dot C hot delta H hot, could also be M dot C cold delta C cold, right? That's the Q. The Q leaving the hot is the same exactly as the Q going to the cold fluid. And Q dot max is always M dot C minimum, whatever the minimum of them, multiplied by T hot N minus T cold N. That is the maximum range that you can imagine. This is the method, all right? And so if he asks for the Q, we come from the x-axis with the number transfer unit and epsilon, and C, we go the epsilon, and then we get the Q. All right? If he asks for the area, when we know the epsilon, we go to this guy, and then we go down, read the x-axis. All right? Does it make sense? So those three guys related to each other. The epsilon, the C, and the number transfer unit. All right, so let's read now. So this is a cross-flow heat exchanger, just like our project. All right? To be designed for waste heat recovery, just like, not really just like our project. Our project is, we are using it to heat a cold fluid, but now they are using it to take the heat from a hot fluid. Okay? They don't want to leave this hot fluid without using some of its energy first. So the hot fluid is coming, it's 5 kilogram per second of exhaust gases, so that's M dot hot, that's 5 kilogram per second, and it entered at 240 degree, and it's supposed to be cooled to 120 degree, all right, by 5 kilogram per second of air supplied at 20. So note that it's not really counterflow, it's not really barrel flow, it's cross flow. Okay, so a cross flow, one of them would be coming like this, and the other one would be leaving like this. So when I'm plotting it like this, I don't really mean they are parallel flow. I'm just saying here's the inlet, here's the outlet. Okay, but they are counter flow. So the air is also 5 kilogram per second. So M dot cold is 5 kilogram per second, and he's supplied at 20 degree, and we don't know how much he will go to, but we can calculate this easily. How can I calculate the exit temperature of the air? Anyone? Right, if I find the Q dot from the hot side, and I say it's M dot hot, CB hot, delta T hot, that must be the same Q dot on the cold side. M dot cold, CB cold, delta T cold. But I have to have CP for both of them. He actually said the heat exhaust gases CP is 1200, and of course for air I can just open my table in the textbook and get for the air, and CB for the air is 1010 joule per kilogram Kelvin. And I just have to say one thing about this, that the CB is actually function of temperature. If you open the table, you'll find that the CB is function of temperature. So the CB should be done at a good temperature that represents the flow. Not really the inlet, not really the outlet, but maybe the average, right? So that you can make the problem more accurate. All right. So you'll be able to get the Q dot for both of them. So what does he want from us? He actually gave us the U. So U was given. Right. That's the only thing that's missing, right? He gives us everything, so the only thing that's not given is the area. So U is 40 and required is the area. Alright, so what's the plan? How we can get the area? And by the way, for that cross flow, he need to tell us, are they mixed or unmixed? Or one of them is unmixed. So he said the required heat transfer area if both streams are unmixed. So when I open the textbook for cross flow heat exchanger, I will pick the equation that has both fluid unmixed. Which one is that? Cross flow and so cross flow C max mixed, C max unmixed. Actually, there is another equation. It will have with both of them unmixed. Okay. So the chart will be this one, cross flow with both fluid unmixed. Alright? So this is the one that we are going to use. So chart number E. Okay, so we are going to use chart number E because both fluid were unmixed. Okay, so what's the plan? How are we going to get the area? Anyone? So obviously I need to come down here, right? So that I can read the x-axis where the area is. So to come down here, what do I need? I need this. Alright? I need to know where I'm coming from. What is the effectiveness? So I need Q over Q max. Alright? So actually, since we know that both of them have 5 kilogram per second, what will really determine who has m dot C minimum is just the CP. Right? The smallest CP is the one with the m dot CP minimum, which is the air. The air has CP of 1010. This guy is 1200. So the cold side is the m dot CP minimum. So in this equation, I can just cancel this with this. So the effectiveness is delta C cold over T hot N minus T cold N. Okay? So it turned out that epsilon is the 6,000 over 5,050. So I end up calculating the m dot CP for both of them. So 5 times 1200 and 5 times 1011 and 240 over 120 over 240 minus 20. Why did I use it on the hot side? Because I didn't want to get the T air out. So this, I guess it's a little bit shorter. You can do it, you can calculate the effectiveness from either one of them, right? But if you calculate it from this, you will have to get T cold out. If you calculate it from this, you already have the delta T hot. Alright, so we know the epsilon. It turned out to be 0.6. Okay? C minimum and C max, we got it. That's basically the ratio between the 550 over the 6,000, or actually the ratio between the 1200 over the 110. Right? C minimum over C max is basically the 110 over the 1200. Just remember, the C is not just the CP. That C is m dot CP. Right? But since m dot is the same, they cancel out. And so we just go ahead and read the effectiveness. So the effectiveness turned out to be, you will read it as 2. Right? So if 2 is equal to UA over M dot CP, and you have the U 40, and you have the M dot CP minimum, you can get the area. So the area turned out to be 253 meters square. Question? So again, the whole method is basically this chart, and either you're trying to come up, calculate something from here, the U or the area, or you are trying to calculate the Q so that you can get the delta T at the exit. So that's the regular procedure, or the normal procedures, that you know the heat changer, and you know the M dot and CP. You're just wondering how much the temperature of both of them. You don't know T hot out, you don't know T cold out. You don't know how much Q will be transferred through this thing. And that's when this method becomes superb. Right? Because you will read the area and U and M dot CP from this x-axis. You will come here at C max, you'll come up with the epsilon, and that will tell you the Q of the hot or the cold. And you can come up with how much heat will be transferred or what's the exit temperature. You had a question. What's your name again? I'm sorry. Martin. Right, so the CB air is from our textbook, from the charts, the table at the back for the air. So that's a good question. And so you know that if we do it at 20, that's probably is not a good idea, right? Why it's not a good idea at 20? Because you know the air will get hotter. You don't know how hot it will get yet, but you know it will get hotter. And so if you really want to do this accurately, you assume what is the T mean, and you calculate CB at this temperature. And once you come up with the temperature at the end, you go and say, well, actually the T average was not what I assumed. The T average is something else. Will the CB of the air become any way different from the number I used? And if the difference is big, you go again with the right CP. And you do the problem one more. This is to be accurate. If you want to just solve it very roughly, you just do it at 20. But you know that 20 is really wrong. At least, do it a little bit higher. Because that show, even if you don't go in the exam, talking about the exam now in the final, even if you don't have the time to do another iteration, at least it shows that you know that the CB should be evaluated at the average temperature, and that average temperature is probably higher than the inlet temperature because that air is going to get heated inside. Jesse had a question.
Yeah, I followed you up to finding epsilon, but whenever you're trying to find the two on the graph.
Right, so that, what we are after? We are after the area. We are after the value in the x-axis. I want to find out where I am on the x-axis. I want to find my U, A, M dot, C minimum, which will end up being 2. Okay. And if I find this, then this I can get the area because I know the U, I know the M dot C. Right? Yeah. M dot C minimum, I know it. Okay. It's the air. It's 5 times 1010. It's basically 5050. So how can I come here? I need to find my curve. I need to find my epsilon. So knowing the epsilon, we did find the epsilon, turned out to be 0.6. Actually 0.648, I'm sorry. 0.648. And C minimum over C max should be 1000 over 1200. How much is that? 0.84. So chart E, 0.84. When you come with X equal 0.648, what do you get? All right, we are done. Okay. So again, on this chart, it would be like this. So we said the effectiveness was 0.648. So this is 70. 648 would be here, around this.
Right. I think what confused me is that 0.6 because it's 6.4.
Okay.
So it was a little bit higher than.
All right. So 0.84 is like something like here. Mm-hmm. This is 0.75. So. And I realize that reading this chart is not really that easy. And that's why the equation is probably a better choice. All right? Questions?